It is a beautiful Tuesday afternoon, and that can only mean some physical sciences. Yes, welcome to the show. My name is Tobile Nkosi. Thank you so much to Liberty for sponsoring our show. Please, if you haven't done it yet, download the Tenfold education app and bring through all those questions. If you haven't done it yet, please download the app and make sure that you send through your questions so we can answer them. Make sure that, or you can actually stream it live and so forth. So without wasting any more time, stay tuned and let us do some physical sciences. So in today's show, we're actually doing a little bit all about the equilibrium constant, or what we call Le Chatelier. So I've got some questions from you guys that I'm going to answer. I'm going to try and answer as many questions as possible, also go into as much detail to the questions as possible. And you'll see that I'm going to continue repeating the same thing over and over again so that you'll see how we actually link the concepts to how you answer the questions. So the first question that I have for today is from Matsiriso Mafereka. And Matsiriso's question is in here. So she says, we've got carbonyl bromide, which is COB, and it decomposes into carbon monoxide and bromine according to the following equation. Initially, we have COBr2, which is sealed in a 2 cubic decimeter container. So this is the volume of the container, and it is heated to 73 degrees Celsius. They could have also used Kelvin. The reaction is allowed to reach equilibrium. Now, when we reach equilibrium, we know that it has to do with the forward and the reverse reaction, as well as the consumption of the reactants and the forming of the products. And this happens at this temperature. The equilibrium constant for the reaction at this temperature is 0.19. Now, remember, when they say equilibrium constant, that means they've given us our Kc. Question 6.1 says we must define equilibrium constant. Now, how I always stress it out, there's a big difference when you have to explain something, when you have to define something. When you explain something, it's based on what you understand. So it's based on your discretion, right? So there's technically, when you explain something, that's not really a wrong and right answer. When you are defining something, especially in physics or in chemistry, it means that that whole definition must always stay the same. The examiner is looking for certain words that you are using. For example, instead of saying the size of something, in physics we say the magnitude, and those are the types of terminologies that the examiner is looking for. So let's define the term equilibrium, and that is 6.1. So in 6.1, we need to define equilibrium, and the definition is the stage. Now we know that it is a stage because reactants are being used and products are being formed. It is a stage in a chemical reaction. In a chemical reaction, when the rate of the forward reaction, remember, forward reaction means our products are being used up, and that equals the rate of the reverse reaction, and that is in your products that are being formed, equals the rate of the reverse reaction. So that's a definition. Let's see for how many marks was that question actually. So, okay, we don't have a mark allocation, but usually a definition can be 2 to 3 marks, so keep that in mind. So let's continue. So it tells us at equilibrium, it is found that 1.2 grams of CO is present in a container. Now, already the examiner is trying to spice this question a little bit up, because in grade 11, we were taught how to move from grams to moles of a molecule. So what you need to do here is first convert these grams into the moles of CO, and then you're able to find what's in equilibrium. Remember, when we are working with the Kc, we work with moles and we work with concentration. We don't really work with grams, we have to convert the grams. So that is step number 1 that you need to do, and then you're able to find out what happened in equilibrium. So first things first, I would draw or write out this whole equation. I'm going to show you how to do the table, and then we're able to find the question. So the question says we must calculate the equilibrium constant of COBr2, which is this one. So step number 1, we first have to draw the whole table. So I'm going to work on this side so that I actually have the whole table. Or let me actually work on a new slide. So for 6.2, I have the equation COBr2, and that is a gas. It's a reversible reaction. So then I have CO here. I've got CO, which is also a gas, plus I've got Br2, which is then also a gas. Now they've told me that the volume is 2 cubic decimeter. I actually like writing it here so that I know. My Kc was also given, which was 0.19. That was also given. Now some information. I was told that at equilibrium, I have it in grams of CO, right? So now let's see how many grams of that we were given. We were given 1.12 grams. So what we first need to do with this CO that we are given here, I must find big M. So the big M of CO, I know that C on the periodic table has got a molar mass of 2, whereby oxygen on the periodic table has a molar mass of 16. 12 plus 16 would give me 28 grams per mole. But I'm not done. In grade 11, this is where this formula is introduced. We've got N is equal to small m over big M. The difference between the two, these are the grams that you're given, and this is the molar mass of the molecule. The mass that we are given is 1.12. The big M, the mass per gram per mole of the molecule, is the 28. Now let's find out how many moles are that. I'm going to put this in my calculator. So I'm going to say 1.12 divided by 28. Let us do that. So that's 0.04. So when we have 1.12 grams, it is equivalent to 0.04. The small n means mole. Remember, capital N means newtons. Do not get that confused. So now I have my moles. However, I'm not done with my table. I use this table. Now, it's very crucial that you can use any method that your teacher shows you. There's a couple of methods that some use the ICU, some use the START, some use the IEC, so it depends on what table you're using. I'm going to be using this table, but more or less, it's more or less the same thing. This is how I do my table. The first thing, I say, this is what I initially have, this is what I've used, and this is what I have at equilibrium. And then I write down my ratios. I'm looking at the numbers in front. If there is no number, it means there is a 1. This means this is 1 mole. I produce 1 mole of this. I produce 1 mole of this. And then I'm also told that, remember, this is at equilibrium, and this is at equilibrium of the CO. So at equilibrium of CO, I've got 0.04. Let's add on to something. These are my reactants. My reactants are being used up, meaning they get less, so we subtract. My products become more, so I have to add. But initially, we have no products when we start a reaction. Now think about it. If I had no products at the beginning, I must have added something to get to this. So it means I used 0.04 and 0.04 because it's a mole ratio of 1:1, which also means I've also used 0.04. But I don't know what is at equilibrium because I don't know what was started here, right? That's what the question is asking me. We need to calculate the equilibrium constant of the COBr. That is the one I don't have. I do not know this one. So you can call it X or you can call it COBr2. I don't know the equilibrium constant here. I know whatever I used was 0.04 because there's a mole ratio of 1:1. Hypothetically speaking, if this mole here was a 2, if 1 mole is 0.04, it means that 2 moles would have been times 2. So this one as well, 0 plus 0.04 means I have 0.04 at equilibrium. But however, we are not done. We are told that it is at a volume of 2. So I'm going to divide each part of this by 2. Dividing it by 2 on this side, I'm going to get 0.02 and I'm going to get 0.02. So that's my step number 1 that is then complete. I still do not have my X. I'm just going to take this off so that I don't have to move to another slide so that you guys are still with me. Now from this side, I'm then going to calculate my Kc. I'm going to do it the long way around. I know that when I do my Kc, I first have my products over my reactants. Now, something to just stress upon, which most of you guys forget. Remember, when you do Kc, you do not put your solids. If there was a solid, then you do not include it. You can just put a 1 there, but otherwise you do not put your solids. We do not include solids when we're doing Kc. In this case, we only have gases, which makes sense. So my products, we have to use these square brackets because this means concentration. Now remember, if there was a number in front, it would then become an exponent. These are my products over my reactants, which was COBr2. My Kc was given, which is 0.19. Now all of this is just mathematics. I'm just going to move here so I have a little bit more space. I'm going to have 0.19 is equal to the value of CO at equilibrium and Br is this number here and this number here. So I'm going to say 0.02 multiplied by 0.02 all over. Remember, this is unknown, so you can keep it as COBr2 or you can write it as an X. I'm just going to write it as an X because it's just going to make it much, much more easier. I'm going to multiply the top part. So I'm going to say 0.19 is equal to, let's do the mathematics at the top part. Clear that. So I've got a bracket. I've got 0.02 multiplied by 0.02, and that gives me 0.004. So at the top part, I'm going to have 0.0004 all over my x. I am solving for my x. There's an equation sign. I'm going to cross multiply. This multiplied by 1, this multiplied by x. On this side, I'm going to get 0.0004. Anything multiplied by 1 remains itself. On this side, I'm going to have 0.19x. Mathematics. If I'm looking for x on itself, I divide both sides with what is irritating my x. In this case, it's 0.19 because I am trying to get rid of that. And then I'm going to find my value of my x. Now, let's use our calculator again. So then I can say, remember, this and this will cancel. This and this will cancel, so I'm only left with this side. So where's my calculator? There we are. So then I can say 0.00004. How many zeros do I have? Let's just backspace. I have 3. All over 0.19 will then give me my value of x, which gives me 0.002. Remember, now I have to leave it to 2 decimal places, but I'm going to leave it I'm going to do it differently. Let me write the whole thing though. 0.5263. I'm going to move my comma. 1, 2, 3. So I can then say the value of x is 2.1. The 5 will round off the 0 as a 1, and that is times 10. I've moved my comma 3 times to the -3. Remember, when we are talking about the concentration at equilibrium, concentration is mole per cubic decimeter. Remember that concentration is C is equal to N over V. N is your moles, V is volume per cubic decimeter. So this will be moles per cubic decimeter. So that will then be the value of Br at equilibrium. Let me just write it here. So this is the answer that we were looking for. So here at equilibrium, we have 211 times 10 to the exponent 3. And voila, that's the answer that we required. Usually a question like this can go up to 6 and 7 marks. So make sure you actually get this one right. And then we have this one. We have the next question says, calculate the percentage of COBr2 that decomposed at 37 degrees Celsius. Now let's talk about decompose. When something decomposes, I want you to think about it as if it got used up. We had something, right? And then some of it decomposed, meaning it got less. Initially we had something, decomposes, and then we have a final product. So with this one, we have what we have at equilibrium. We do have what we have used, but we don't know what we had at the start. Remember, when something decomposes, we have to have initial. We need to know what was used so that we can then find at equilibrium because it was used up. It decomposes. I want you to think of it in that sense. So calculating the percentage, this is how I would tackle it. So this is 6.2.2. So I just want to write some steps here. So for percentage decomposition, if you ever forget it, what I would say, firstly, you need to find out what you had initially, the initial amount. Once you have the initial amount, you also need to find the final amount. And then between the two, you're able to know what happened. Like in physical science, we always say final minus initial. That will give you the decomposed. And that will then be over the initial amount. And then we can multiply that by 100. I just want to go back to what we answered here. So now we do have this. We do have what was used, but I do not know what was my initial. If this is what I had at the end, And this is what I've used to find the initial part. You must then add the 2. And then we're able to find the initial amount. Just take this off so that we can find that. That's step number 1. This was a little bit tricky, but not so bad. So first things first, let's find the moles. So I can say finding the moles of COBr2, I know I have the concentration at equilibrium. It was at a certain volume. The concentration is the one that we calculated, which was 2.11 times 10 to the negative 3 times the volume of the container, what we were told was 2. Let's use our calculator to see how much we're going to get here. So let's see what we get. I always put it in brackets. I always think it's much more safer. Times 10. Let me use it like this. Let me use this one. Let me use the 0.002105. So you can use either one. It really doesn't matter. Times that by 2. Then I get this value here, and then I'm able to move my answer. So I think this just works so much better for me. 1, 2, 3, and then I'll say times 2 to the 21. So let's see what answer I'm going to write here. So I'll have 4.21 times 10 to the negative 3, and this is my moles, right? So this is then the moles that I have. But now let's find the initial moles. So if I say C of COBr2, the initial ones. If I'm looking for initially, what do I have? I know that I've used 0.04, and where do I get this one? This is the one that I get here. This is what was used. Where did I get this answer? It is a mole ratio of 1:1:1. So we used this throughout the whole number. So I've got that one, and I'm going to say plus to the initial ones of 4.21 times 10 to the negative 3. So that is then your initial moles. Actually working it on my head, I'm going to get 0.044 if I move my comma, and that gives me my answer in moles. Now let's find the percentage that was decomposed. So percentage decomposed, and always remember to actually write a formula so that your examiner actually sees what you're doing. So I'm going to take my initial amount, well, my decomposed amount, which was 0.04. 0.04 was my amount, and then at the bottom I need to take my initial amount, which is the amount I just calculated here, which was 0.044. Just to give you guys a little bit of a tip, if ever you feel like this answer you're not so sure about and so forth, make sure that you actually substitute it correctly moving on, because the examiner will give you a mark for continuous assessment. So they'll say, oh, Shay, man, but she didn't really kind of sort of get it right, but because she knew that this initial amount must be used in this place of the decomposition formula, then you might get a mark for continuous assessment. So make sure that you keep that going. So then I've got this amount, and then I'm going to multiply that by 100. So let's see what percentage do I then get. Let me just move my calculator down here. There we are. So I'm going to have 0.04 at the bottom. I'm going to have 0.044. Move it there. Move it. Okay, let me just do it like that. And then times that by 100. So I get 90.91. Remember, this is a 9. It'll round off the 0 and change that to a 1. We usually leave our answer to 2 decimal places. So then I will get 90 point, now I forgot what answer we got there, 90.91, 90.91. And remember, percentage means you need to have a percentage. Another trick to give you with this, most of the time the examiners, because it depends where you round off. I know some educators say, please don't round off your answer until your final answer. And then some teacher says, no, man, it's fine. You can round off to 2 decimal places as you move along. So if this is your final answer, the examiner might give you a range. Maybe they might start marking from 90.45 all the way to 90.95. So they'll give you a range, because we do know some people use exponents, some people use decimals, and some people round off to 2 to 3 decimal places. So, or some people even round off to the nearest whole number. But to my advice, guys, make sure you only round off your final answer to the nearest whole number, or 2 decimal places only at the end. Then you are more or less to be at a more accurate amount. So the percentage that was decomposed, this is the amount that we got for this question. Let's see what other question that we have from this question. So it says, which one of the following correctly describes the Kc value when the equilibrium reaches a lower temperature? Now, something to remember. When we lower the temperature, we reduce the kinetic energy. So I can see this is smaller than 0.9, smaller than 0.9, and so forth. When we decrease the temperature, we affect the kinetic energy, which means then it then must be zero than the Kc. Remember, when we are talking about the equilibrium constant, temperature is the only thing that can then affect the equilibrium constant. When we reduce the temperature, we reduce the rate of the reaction, we reduce the equilibrium constant, and we reduce the kinetic energy of the molecules. Reducing or having a lower temperature and how it affects the Kc, it will be then less than the 0.09, because when we reduce temperature, it means we are favoring the exothermic reaction. Now 6.4 says the pressure of the system. Let's just talk about pressure quickly. Pressure works in two ways. We can either increase the pressure of something, but what are we doing to the volume? We are reducing the volume. So they are inversely proportional. When one is increased, the other one is decreased. So when the pressure of the system is now decreased, when we decrease the pressure, we are increasing the volume. I want you, every time you think about pressure, think about gas molecules. Think of people in this room and we're all moving around, and then the room gets smaller and smaller and smaller and smaller, meaning that the pressure gets smaller and smaller, meaning that the molecules are forced to be closer and closer towards each other because the volume is getting smaller, but the pressure is getting bigger. So this is what's technically happening in a container. So now the pressure of the system is now decreased by increasing the volume of the container at this temperature, and the system is allowed to reach equilibrium. How will the number of moles of COBr2 be affected? Choose only from. Now, if they give you increases, reduces, and stays the same, only choose that. So choose from increase, decrease, or remains the same. Now remember, if the pressure is decreased, it means that we are increasing the space between the particles. So it means that it will then also decrease. A decrease in pressure favors the part with a large amount of moles. I want to go back to the side. This is how I usually work out the whole pressure thing. If you have an equation written like this, I've got 1 mole on this side, I've got 1 mole and 1 mole, giving me 2 moles on this side. So if we decrease the pressure, it will favor the product with a large number of mole gases, which is then on this side, meaning that the forward reaction is then increased, and then the reverse will be done. So now an increase in pressure will then decrease the amount, because we will favor the forward reaction because it has the most number of gas molecules. And I think this was the last bit of this question, and we've actually then explained our answer, but now let's write it down so our examiner knows what we have said. So this is 6.4. How will the decrease of pressure affect? Increase, decrease, or remains the same? It will decrease it. Now remember, when you have to give an explanation in terms of equilibrium and so forth, don't say pressure will decrease because the molecules are more on the right-hand side. It doesn't work like that. You must actually stipulate that when we decrease the pressure, how does the equilibrium then shift? Remember, it always shifts in a way to relieve the stress, and then you have to say how it will shift or where it will shift, and then give a reason why. So we first say decrease, because this was for 3 marks. It will first decrease. The reason is a decrease in pressure. When we have a decrease in pressure, it favors the reaction that produces the larger number of gas molecules and in this case we know that that is the forward reaction, which means the forward reaction is favored. Forward reaction is favored. What I also like telling my learners is that if you're given an answer, to say decrease, increase, or remains the same, and explain your answer. So now we know that we have decreased it. According to Le Chatelier's principle, when we increase pressure, now you have to tell the examiner what Le Chatelier says. What I always tell my children, always write as though you are explaining to somebody who does not know physics. when we decrease the pressure, the system will favor the part that will have the more gas molecules, right? And that is then how you have to explain it. Make sure that it sounds like a story, somebody's able to relate, and whatever you're answering here explains your decrease, increases, or remains the same based on Le Chatelier's principle or based on the equilibrium constant. So that is then how you have to tackle a question like this.